Recording has started, and let's begin with gravitation. Thanks. Let's begin with gravitation. All right. Now, as I said before, the reason I actually started, now let me just make a little thingy here. So the first chapter was circular motion, right? And then we have gravitation, then we have SHM, and we have electricity. Now, a lot of people, they go with this as number one and this as number two. It's a choice of the teacher. I believe that SHM is the better choice because we can easily convert CM to SHM just by reflecting CM on a wall, just like I said, just like I told you guys yesterday or the day before yesterday. Now, there's a really fun fact: CM and gravitation and SHM. Now, CM is similar to SHM and it is similar to gravitation, but gravitation and SHM, according to my knowledge, don't really have anything in common. They might have, but like really, really small details. But gravitation and electricity, they are like very similar. I'm going to confirm, but most likely. Yeah, if anyone has their mic turned on, please turn it off because I'm not using a speaker right now. Thanks for telling. Okay, gravitation and electricity, these two are very similar. Now we're going to start off with gravitation, and I'm going to start with a comparison between CM and grav. All right. Now, in circular motion, we studied the turntable, right? Turntable. I hope everyone knows what that is. I mean, we did it a lot of times. This is the turntable. And for this example, just for the sake of this example, I'm going to use a center point here, and I'm going to use two objects. Let's say I have two small objects here. Let's say this is object A, and I have an object B here, right? Two objects. Now, I have a question for you guys. Now, the turntable starts to turn. It starts to turn. Now, this is at time is equal to 0 seconds, right? Let's say that this turntable travels 90 degrees in, I don't know, seconds. So at this point, 2 seconds have passed. Now, are these 2 points gonna be in the same line, or are they gonna be not in the same line? Can anyone tell me, please? Is point A, is object A and object B gonna be in the same line, or is it gonna be like this? Okay, or is it gonna be like this, A here and B here? Okay, same. Now, let's make the same situation, but for the space. I have sun, this is sun. Now let's make, okay, what's the first planet after the sun? Can anyone remind me? I mean, basic science. What's the first planet in the solar system? Yeah, Mercury. I don't know what the color is. Let's just use a brown color. This is Mercury. Let's say we are comparing Sun, Mercury, and Venus. Yeah, Venus. So let's use this color. I don't have gray. Okay, now let's say both of them are in the same line at the moment, right? So both of them are at the same line at time is equal to 0. Now tell me this thing. Let's say, I mean, time period in solar system, that's like in years, like 365 days, I don't know, example. Now let's say, I don't know, 300 days have passed, 300 days. Now, after 300 days, it's a question for you guys. Are both of the planets gonna be in the same line? Come on, guys. Are both of these planets gonna be in the same line? Why? Can anyone answer this question? Why? Why do you think that both of these planets are not going to be in the same line? Okay, that's a valid point. But let me remind you that even for the turntable, the velocity was different. Did you forget it? Point A has lesser velocity and point B has greater velocity. So velocity is not really a valid argument. But then again, bro, look at this. In the turntable, point B has to travel larger distance. So both of these, okay, Shiza, good answer. Different time periods. Now, when I was learning this chapter in my school, even my teacher said the same thing. Turntable, this is one system. This is one system, right? One system. But space is not one system. So M, Mercury, Sun, S, Venus. These are two systems, Sun and Mercury, and Sun and Venus. Both of them have different conditions, different aspects, because these two are different systems. This is not one system. Now, if I would ask you, but basically, before I ask that question, for all of the planets and the sun, these are all different systems. Okay, so how many planets do we have in the solar system? Just a random question. That's what I wanted to ask. Guys, did you do science seriously? Yeah, 8 or 9. I mean 8. Yeah. So in the solar system, generally we would have 8 different systems. But if we consider moons, yeah, if we consider moons, right? Moons, that's going to be more systems. So let's say generally we have 8 different systems in our solar system. Why is it that? Well, we're going to discuss it in this chapter. Now, I'm going to switch this thing to Earth and Moon. Now let's make a little nice Earth, okay? This is Earth, right? Earth. Where's my pen? Okay, this is Earth. And I know that I have Moon here. Let's use, I don't know, this color, right? This is Moon. LOL, just a second. Okay, this is Moon. Now, I know that there's a force binding these two things together. Why is it that Moon rotates around Earth? What is it that makes Moon rotate around Earth? Come on, basic science. Can anyone tell me what makes Moon rotate around the Earth? Exactly, gravity. Or we can also say centripetal force. Why? Because I mean, when I was teaching the horizontal circle, I clearly mentioned that one of the best examples of circular motion, specifically horizontal circle, is the space, the sun and the earth, or the earth and the moon. But first thing comes first. We have to show that there's Fg. Now, this gravitational force is called Fg. But didn't we learn in AS that every action has equal and opposite reaction? So, okay, so if there's a force acting from moon to earth, can I say there's a force acting from earth to moon? Now, we will not be discussing this force, but this is just a general question. What if both of them have a force acting towards each other? Why is it that moon is rotating around the earth? Why isn't it otherwise? Why isn't the earth rotating around the moon? Both of them have the same force acting towards each other. So my question for you is, why is it that moon is the one to rotate? Okay, that's the right answer, Basil. In AS, you should have learned that basically the smaller mass, it attracts towards the earth. Like, look at us and look at Earth. Earth has a mass. We have a mass. Why are we falling towards the earth and not the earth falling towards us? I mean, that's a very weird question. That's because we have a smaller mass. Smaller masses, greater masses attract smaller masses. That's why sun is at the center, because sun has the largest mass. So these are some basics which had to be clear. Now, I know that since moon is rotating around the earth, I can clearly make a circle here, and I can say that this is also an example of circular motion. So, I can confidently say that we have a centripetal force acting towards the center, right? And I can say that FC is provided by FG, right? So, by the way, whenever I'm going to answer your question in a minute. So first, listen to this. Whenever you're doing any kind of question, I'm going to show you exactly how, but you have to always specify that centripetal force is provided by Fg. So I can say that basically my centripetal force is actually Fg, right? So Fc is equal to Fg. Now I'm going to ask your questions. Okay, so Shabana, why is it so? What do you mean by why is it so? Do you mean the centripetal force or do you mean the masses? Okay. Oh, listen, Key. For the planets, it's different, right? For the humans, I mean, we are not rotating around the Earth. For the planets and the moons, I would say, it's different. They are attracting each other, but they're not moving towards each other. They're only rotating around each other. I'm not a professional physician. I don't have knowledge exactly what exactly is happening in that much detail. But what I can say is that don't forget that there's an opposite force as well. So sun attracts earth, earth attracts sun. But the overall resultant is that earth is revolving around the sun, right? So in the space, right? In space in general, larger masses are the center and smaller masses rotate around them. But you're going to learn some amazing stuff later as well. It turns out there are scenarios where two planets or two stars, they are rotating together, right? Key, listen, that's a concept of AS. I don't think we should get into that. Basically, in space, larger masses, basically in space. Okay, I'm going to tell you one statement. Newton's third law. We're not exactly attracting Earth, but there is a force, right? As I said, I'm not going to get into that because that's like really confusing. Maybe I shouldn't have mentioned that, but that is a concept. So you can look into it later. Okay, so Shabana, that again is a concept of AS. What I can say right now is larger masses are the center and the small. Okay, I'm going to give you a really cool example. There's a YouTube video which in a very beautiful way explains how space works. So I'm not going to be able to show you exactly what was in that video, but look at this. Imagine that we have a piece of cloth, right? Imagine that I have a piece of cloth here. Now it's not 3D. Let me make it 3D. Now pay attention. This is a very beautiful example of how space works. Imagine that I have this little circle and I have placed a piece of cloth here, right? So imagine that I have placed a piece of cloth here. So all of this is a piece of cloth, right? This is a ring. Let's say this is a ring of some kind, right? I don't know, a table. And this is a piece of cloth. And the piece of cloth, this is a cylinder, okay? This is a cylindrical table and it is hollow, right? So if this cloth wasn't here, you would be able to see the ground. I hope you can imagine it now. So this is a cylindrical table. And what I've done is I have placed a cloth on it. Now, you know that whenever we place something on the cloth, so let's say I have a ball, right? Let's say I have a big ball. Now, when I place the ball, can I say that the cloth is going to go down a bit, right? So it's going to go a bit down. Can you guys comprehend it? Can you guys imagine it? So when you place something, this is a stretched piece of cloth, right? A stretched piece of cloth. And this was an actual experiment, like an official experiment done. I'm going to send you the link to the video. It's a very beautiful demonstration of how space works. Now imagine that we've placed a big ball right here. Now, the cloth is kind of, it's kind of falling in that place. So if I place a ball here, this ball is going to go towards that direction, right? This ball is going to move in that direction. Now imagine that this thing in the center is the sun, and the person who is conducting this experiment, okay, let's make it orangish. Now imagine that this ball, this is the sun, and the person conducting this experiment, he takes a little blue ball and he throws it in such a way. Something amazing is going to happen. You know what's going to happen? This blue ball is going to start spinning around the sun. It's going to start spinning around the sun. Now, it obviously eventually it loses energy and it falls into that, because this is just an experiment. We cannot replicate what actually is. But answering your question, Shabana, imagine that space is this piece of cloth. Obviously, you know that when I place a larger mass here, if I put a lot of small balls here, obviously the small balls are going to go rushing towards that, big mass. So imagine this as us humans. Exactly. Imagine this as us humans, and I don't know, imagine this as the planet. Now I'm going to send you the video right after the class. It's a very amazing video. It cleared up a lot of concepts for me. So I hope this makes sense. Now, I personally, at this moment, this is the best answer I can give you. Imagine space being a piece of cloth. And if you have a larger mass, obviously it's going to attract the smaller masses. So I hope that makes sense. Now, without further ado, let's discuss the actual gravitation. I mean, the A-level gravitation. All right. Now, okay, can anyone remind me, what is the formula for centripetal force? What are the formulas for Fc? We have two formulas. Can anyone remind me? I mean, circular motion, I hope everyone remembers it, unless you have forgotten it in a matter of one chapter. Guys, yeah, mr omega squared. Or I can also say mv squared over r. Now, let's keep this at the back of our minds and let's move it over here. Now, today, I'm going to introduce you a new formula, which is Fg, the gravitational force. It's a new formula, and allow me to introduce that. This is Fg. What is Fg? I mean, just as the name suggests, this is the gravitational force. This is the force that exists between Earth and the sun. So, I mean, let's write it. By the way, I'm not going to write it right away. I mean, we derived Fc, so we're going to do the same for Fg. We're going to be deriving Fg, okay? Now, there's a little relation that I have to write first. So let's start with Fc. I'm going to be using this formula. So just a second. Okay, let me write it. Okay. Now, yeah, it's gmm over r squared, but I want to derive it so it actually makes sense. Okay, let's start. Now, there's a little relation that we're going to be deriving later. For now, I'm going to write it. T squared is proportional to r cubed. Now, a fun fact. What this tells you is greater your radius, I mean, imagine moon, imagine Earth, and imagine Jupiter. So according to this formula, the larger your radius, the larger is going to be your time period. Now, if I were to write it, it would look like this. It's going to be T squared is equal to kr cubed. That is if I remove the constant, okay? That's if I remove the constant. T squared is equal to kr cubed. Now, this statement that I wrote before, I'm going to write it again, okay? The statement was force of gravitation provides Fc. And that's why we're going to be using Fc to derive this whole formula. All right, now pay attention. I'm going to be using Fc is equal to mv squared over r. Now, I know that there's another formula for velocity. Can anyone remind me? So what I'm going to do is I'm going to write FC is equal to m over r, and I want to substitute something into velocity. Okay, general formula. What is velocity? Uh, velocity is r omega, but we're going to be writing another formula here. First, what is the general formula for velocity? What is velocity? I mean, what is velocity? Yeah, distance over time. Or I can say displacement over time. Now, imagine that we're talking about circular motion. What is going to be my displacement? If I'm talking about one circle, what is this distance? What is this displacement? I mean, from point A to point A. So from point A to point A, 2 pi r, 2 pi r, because I'm talking about the distance. Yeah, the circumference, right? So this is 2 pi r. Why did I use this distance? Because we're talking about gravitation, and obviously the motion is also going to be circular motion. So I mean, till this day, I have never seen that planets move like this. Planets move in a circle, so that's why we're using 2 pi r, because 2 pi r is the circumference of one circle. And I know that when we're talking about one circle, the time is going to be the time period. So it's going to be 2 pi r divided by t. So if you didn't know about this formula, remember it. Sabina, can you please tell me, what do you mean? Can you please turn it off? I can move the fig. What do you mean by that? Okay, so explain while. Meanwhile, I'm going to explain the next part. Okay, so I am going to substitute this into this. Now it's going to turn into 2 pi r divided by time squared. Now, can anyone tell me what am I going to get? Okay, now you guys tell me, what am I going to get here? What's going to be my FC now? When I square all of this, can anyone tell me? I know it's going to be a bit hard to write, but I mean, let's do this together. Guys, can anyone tell me, what am I going to get here? What is going to be FC? Come on, just square it and tell me. I'm waiting. Hey guys, I'm waiting for your answer. Yeah, finally. So 4 pi m. Okay, 4 pi squared. Don't forget the square. So 4 pi squared m r squared. Good job. And we're going to get r squared, and we're going to get t squared over here. All right. Now, what I'm going to do is, we did something over here. I have t squared. Do you see this? Why did I suddenly, I mean, in the middle of nowhere, why did I introduce this relation? And why did I say that t squared is equal to kr cubed? Because to derive the force of gravitation, I have to substitute this into this. That's just a condition. Yeah, this is 4 pi squared. Well, what do you mean? Yeah, r squared. 4 pi squared m r squared. Oh, thanks. I get it now. This is not squared. Thanks. Okay. Basically, what I'm going to do now is I am going to put this thing into this. So I am substituting this kr cube into the t squared. What am I going to get now? I'm going to get 4 pi squared. I'm going to get a small m, and I'm going to get an r squared over here, and I'm going to get an r, and I am going to get kr cube. Okay, so Sabina says both are the same. Okay, so Sabina, basically both of these r's are the same. It's just that I wrote it as a small r. Let me change it to the big R. So since I represented r as the big R over here, I should definitely place a big R over here. So let me fix it up. It's going to be a big R. It's going to be a big R. It's going to be a big R. Okay, now 4 pi squared m r squared and k r power 4. Now, when I cancel them out, okay, let's see how good are you guys at math. What am I going to get now? How do I simplify this? I just want to check your math, guys. Let's see. Basic math, come on. What am I going to get now? I have r squared above and I have r power 4 over here. What am I going to get now? Exactly. R squared at the bottom or above? Good job. I'm glad you guys know math. Okay, that's amazing. The reason I did it is because a lot of students actually get confused in the basic maths. So yeah. Anyway, what I'm going to get now is FC is equal to 4 pi squared m divided by kr squared. Now, what we're going to do here is we're going to be changing this formula, and a small magic is going to happen, and we're going to end up with something. Now, yeah, now pay attention. Let's use an arrow to guide us. Okay. Now we're going to be using something over here. First of all, tell me, I know that 4 pi squared is a constant, right? Okay, let's identify the constant values here. Which one of these, which things here are constant? What do you guys think? What is constant over here? Okay, don't you think this is constant as well? So can I say it's going to be 4 pi squared divided by k? So this whole thing is a constant. I'm going to tell you which constant this is. For now, I can say that f is proportional to mm, and it's inversely proportional to r squared. Let me tell you how. Where did the big M come from? And in the formula, the actual formula is Fg is equal to mmg over r squared. But where did the big M come from? Now, a simple statement. By Newton's third law, we must have two different forces. What this means is we have the force acting on, in both directions. So that's why what I'm going to do now is I'm going to write this like this. Fc is equal to 4 pi squared mm divided by kr squared. Now, I know this part is suddenly confusing. Where did the other mass come from? Look, just as I said before, we don't represent it usually. We don't show it on the paper, but Fg is actually acting in both directions. So if this is sun and this is earth, Fg would be acting in both directions, and both of them are the same Fg. So it's acting in the both directions. Why? Because of Newton's third law. Now, since it's acting in both directions, and it turns out it's acting for both masses, we're going to be using another M. There's going to be two M's. Now, how do you know which one is the big M and which one is the small m? Fun fact, the big M is always going to be the bigger mass. That's kind of obvious. The larger, capital letter means bigger mass. Isn't that obvious? Exactly, the sun. So imagine that this thing is the gravitational force between sun and the earth. And earth is the small m, while sun is the big M. Now, I told you guys that 4 pi squared, just a second. 4 pi squared divided by k. What do you mean by 2 of everything? You mean why? Because this r right here, I should have told you guys basically. This is sun, this is earth. Look, this is r. This is the radius. Oh, just a second, let me fix it up. Basically, the radius is the separation between sun and earth. And r, it's the same. I mean, yes, MMR. By the way, if this question didn't come to your minds, I'm going to answer it right now. Masses are supposedly constant, radius is the same. So how come we have a relationship between this and this? Because this is a general equation. We're not talking about sun and earth. We're talking about the whole universe. I mean, the whole space. There's a lot of planets and there's a lot of different separations. That's why this is a relation. If I have larger mass, I mean, if the product of these masses is larger, my force is going to be larger. If the radius is smaller, the force is going to be greater. Okay, so Eliza, why didn't we get two of everything? Because first of all, 4 pi squared divided by k, that's a constant, right? And the radius, I mean, it's the same separation. If we're talking about sun and earth, both of them have the same separation, right? But for the masses, it was crucial because we have two masses. We don't have one mass. I hope this answers your question. Okay, I am glad. Okay, Shabana, let me answer that in 30 seconds. First, I'm going to tell you what do we get here now. Now, look, this thing, 4 pi squared divided by k, this is the legendary g. This is the gravitational constant g, and it's a fixed value. This is a constant. So this is equal to 6.67 into 10 raised to power 11. By the way, you're going to have to remember it. There's an option for you to find it at the beginning of your paper, but it's always convenient to memorize it. So 6.67 into 10 raised to power minus 11. Let me make it a bit cleaner. Okay, 6.67 into 10 raised to power minus 11. And that's the gravitational constant. So it's called the gravitational constant or gravitation constant. Call it what you like. Okay, and then we finally get Fg is equal to mmg or gmm. Okay, let's go with gmm. Gmm over r squared. Okay. Okay, Shabana, answering your question. I hope you guys have noted the right side. Can I erase that? Can I erase this side? Let me show you which one. Are you guys done noting down this side? Okay, that's great. I would like to explain this thing over here. Okay, Shabana. So let's say I'm talking about sun and earth. Okay, I'm talking about sun and earth. Earth is smaller than sun. Let's make sun a bit bigger. Now, imagine that this formula right here, I finally got Fg is equal to Gm over r squared. Now tell me this thing. Let's say I have now one mass. First of all, how do I know what mass is this? What is this mass? See, I have two planets. What is this mass? Okay, like let's say this is sun, right? Now, if I say this is sun, okay, if I say this is sun, then what I'm saying is that sun is attracting earth over here. But if I say I have one mass and I have one separation over here, r, then what I'm saying is that, this person Newton, he never existed. This is all fake. Why? Because what I'm saying is there's only one force. I am saying that there's only one force. When I say that there's only one mass, if I say that I have one mass in this formula, I am denying the fact that Newton ever existed. Why? Because Newton says every action has equal and opposite reaction. So, yes, Fg is acting here and Earth is rotating around sun. It's revolving around sun. But you cannot deny the fact that there's another force over here, and this is Fg as well, by Newton's third law. And that's why, since we have two forces, Fg and Fg, acting here and here. That's why we have two masses. I hope that makes sense. Now, if you would ask me, okay, so FG is here and FG is here, so shouldn't they cancel out? Then tell me one more thing. I am standing on Earth. Okay, I was literally about to answer that. So now your next question would be, okay, so FG is acting there, FG is acting here. Oh, so shouldn't they cancel out? Like, why is the Earth even attracted to the sun? Okay, tell me one thing. All right, so I know that Earth is attracting me, right? I know that Earth is attracting me, right? I know that there's a force acting here. And let's continue where we left. Okay, I have started the recording, and yeah, let's do this. Okay. Now, one word answer, AS concept. But I'm not going to leave it just yet. I'm going to see what I can do. Okay. I know that there's an FG here, and I have an FC, and this FC is this FG, right? Okay, so I think this was asked by Shabana. Yeah, I am speaking right now. Okay. Shabana is here. All right, just a second. Let me clear this. Okay, this resultant force is FC, and this is FG, and this is FG2. Okay, so Shabana, answering your question. Your question was, okay, I have FG acting here, and I have FG acting here. So how in the world do I even have a resultant force? Well, one line answer, Newton's third law. And that, my dear students, is an AS concept. But I'm still gonna give you a little answer. Just give me a second, I have lost my screen. LOL. Okay, I'm back. Now, imagine that I'm standing here on Earth. All of you have studied about this concept of W and normal reaction, right? So if you're gonna ask me, why don't these two cancel out? Why don't you ask in AS that if I have a W here and I have a normal reaction here, okay, so there's N here. So with this logic, why am I on Earth? I should be flying like Superman, like, oh my God, why am I even standing on Earth? If N and W, they're equal and opposite, how am I even standing on Earth? I should be flying, like, yeah, I should be flying. Now, I hope this answers your question. That's basic Newton's third law. You know that there's W here, and you know that there's an N acting in the opposite direction. Just like that, there's an FG here, and there's an FG here. They're equal and opposite, but resultant force is here. Just like on Earth, I am standing on Earth. If your concept, if this way of thinking, if this was right, we wouldn't be standing on Earth right now. We would be flying. I hope this makes sense. So if you don't understand this as well, I recommend revising AS. It's not going to take long, just a little search or a little peek in the notes, and I promise it's going to be clear. Okay, so one line answer, Newton's third law. Why? The law itself states. Okay, but the resultant FC is here, and we don't usually make this force because we are interested in this, right? And I just derived, in fact, I proved that FG is mmg or gmm r squared divided by r squared. Okay, does this make sense, everyone? Does anyone have a confusion similar to this or related to this? What about the rest? Okay, that's amazing. I'm glad. And Shabana, was I able to clear your confusion, or are you still confused about this? If you are so confused, I really recommend looking into this concept of N and W. Aisha, you just raised your hand. Do you have a question? Or was that a mistake? Okay, no problem. All right. Now, at the beginning, you know, very confidently, I wrote one thing without literally any background. That it is kind of unfair because I didn't teach you this at all. I mean, you would be like, okay, so where in the world did this come from? Where in the world did this come from? It's a very funny thing. To prove FG, you need this. But to prove this, you need FG. So I'm erasing everything. And before we do this, just like we define everything, just like we defined SHM, just like I defined FC, just like I defined, uh, what was the formula? Yeah, just like we defined FC and the other forces in circular motion, and we defined SHM, we have to define the gravitational force. So in your paper, it's a very common question. So make sure you memorize this by heart. And trust me, when you do a lot of past papers, it's going to be the easiest question you ever did. I mean, you ever do or you ever did. So define the force of gravitation. Yeah, gravitation. Or it's also called Newton's law of gravitation. I mean, there's two names, right? It's the same thing. Don't get confused. Just imagine if I had told you that it's force of gravitation, and in the paper it's like Newton's law of gravitation. It's the same thing. They just want to confuse you guys, right? But we warn you beforehand. So I know that G is the gravitation constant. Now, before we actually write the definition, just like we did for 1 radian, I have to explain you the concept. Now, I know that this is my, what am I writing? Gravitation. The gravitation constant. And I know that mm, these are point masses. Oh, by the way, in this chapter and even in electricity, we assume that this was Earth and Sun. But in this chapter, we're talking about stars. And you know that stars are like really, really far from each other. So in this chapter, we talk about stars. We talk about force of gravitation between the stars. Now, obviously, since the stars are so far from each other, they're just going to have, FG. They're not going to have a revolution around each other. So that's why we call them point masses, because the distance is really, really far. That's the common way of us talking about these. By the way, for Earth and Sun, this happens. But for stars, we're not concerned about whether they're moving closer to each other. But in the paper, you're going to see a lot of questions like this. So you have a star here. They can make it like a circle. They can make, a dot, and they're going to ask you that we have 2 point masses, two stars, really, really far from each other, and they have FG between each other, and you have to find this FG, right? So just telling beforehand. Now, radius is the distance between two masses. So distance between two masses, the two masses. Now, just like I usually do, I am going to tell you the actual definition. In the paper, for some reason, you have to specify that these are point masses, and there's an actual mark for it. So the question itself is of 2 marks. I haven't seen for 3. It may be for 3, but it's for 2 marks, right? And one of the marks, that's for you to specify that these are point masses. Now, I know that in this formula, Fg, mmg over r squared, I know that there's 2 relations, right? I know that there's only one constant. I know that g is constant. So I can say that Fg is proportional to mm divided by r squared. So it has an inverse relation and it has a direct relation. So what we're going to write is Fg, the force the force of gravitation is proportional to the product of masses and inversely, by the way, don't write it just yet. I have to add one thing here, that the point mass thing, the product of masses and inversely proportional to the square of their separation. Now, if you write this, you're going to get 1 mark. Why? I mean, I have to confirm again if it's 3 or 2 marks, but you're going to lose 1 mark, and that's confirmed because you didn't mention point masses. Now, it doesn't always happen, but usually that's the case in the mark scheme. So you're going to have to write the force of gravitation. By the way, people don't tell this when they're teaching you the concept. I'm telling you this out of my topical experience because a lot of questions literally stripped me of my rightful marks just because I didn't mention point masses. So you can say the force of gravitation between 2 point masses. Now, I also tried doing one thing. I tried saying product of point masses, but I just think this kind of sounds better. So the force of gravitation between 2 point masses is proportional to the product of masses and inversely proportional to the square of their separation. Now, most of the definitions are just F proportional to masses and inversely proportional to separation. But to be on the safer side, so you don't lose any marks, do mention this because a lot of times it's clearly mentioned, it's explicitly mentioned that you have to mention point masses. All right, I hope this makes sense. Now, right after this, we're going to be deriving this formula, the t squared and r cubed 1. Yeah, Sabina, the definition you wrote, that also sounds kind of good. So good job. That also sounds cool. That also sounds cool. So yeah, you can rephrase this in your own words. Okay, is everyone done with this part? Is there any confusion? Okay, why the distance is represented by r? That's a good question. I kind of never thought about it, but I guess that's because if you have, I guess because if you have sun here and you have earth here, it becomes like this, right? It becomes like this, right? And at that circular motion, you have FC. So you know that in this motion, if we kind of compare this to a turntable, this would be the radius, right? So that's why. I hope this makes sense. That's the reason why. Yeah, the orbit. And in a lot of questions, yeah, thanks. So in a lot of questions, they don't show the whole circle. They just show that there's 2 point masses and yeah, just like this, yeah. And the smaller mass is gonna supposedly be revolving around that. Okay, I hope everyone is done with this. Are you guys done with this? Can I clear this with a single click? Okay, that's great. Now, let's get to the point. Where in the world did this thing come from? Well, let's talk about it. Now, I told you that gravitation is also a kind of circular motion. So, just like always, force of gravitation provides. By the way, in the paper, if you write this, unfortunately, you're not going to get the mark. Why? Because they want you to write this statement. You can write FC is provided by FG, but it's always better to write like this. Like you can write force of centripetal force is provided by force of gravitation, and you can also say force of gravitation provides the centripetal force. But you can also represent this as FC and this as FG. It's your choice. Then you're going to write FG is equal to FC. Okay. Now I know that FG is GMM over R squared. And I know that FC is mr omega squared. Now, why am I using mr omega squared? Because I want to prove t squared proportional to r cubed. There's no velocity there. I don't need velocity right now. That's why I'm doing this. So it's going to be mm is going to get canceled out. And I'm going to get gm is equal to r cubed. And I'm going to substitute omega with 2 pi divided by time because I need time, right? The square. And gm is equal to 4 pi squared r cubed divided by t squared. And finally, I'm going to end up with t squared is equal to 4 pi squared divided by gm r cubed. Now, this thing is a constant. This thing is constant. And that's why I can say that t squared is proportional to r cubed. And this, ladies and gentlemen, is called the Kepler's law. This relation is the Kepler's law. So if in the paper they suddenly ask you, what is Kepler's law? You can just mention this thing. And if they ask you to derive the Kepler's law, which in most cases they're just going to give you some information and you can finally derive this, right? Does this make sense, everyone? Do you understand it? I know it's kind of weird that to prove FG, you need to know this before actually proving this. But that's just when you're learning the chapter for the first time. Now you know both of the things, so you can do both of the things. So if you want to find FG, just do what I did. And by the way, to derive FG, to derive this, there's a lot of different ways. But the ways I'm teaching you are the ways that my teacher taught me. Maybe other teachers teach other ways, so don't get confused if someone is using a completely different way. It's just a choice because the world of science is kind of flexible. Okay, if note this down, and this is the last thing we're going to be doing for today. Tomorrow we're going to be getting more into gravitation, and we're going to be doing more questions, more concepts. So once you're done, tell me. I can erase this, and yeah, no problem. Okay, I'm glad that everyone is done. What about the rest? I just have like 1, 2, 3, 4 answers. Okay, that's amazing. Have a nice day. If you haven't solved that other question, the last question of SHM, solve it. And inshallah, see you all tomorrow. Tomorrow we're going to be doing more gravitation, and this chapter is a bit lengthy, so it's going to take a while. But yeah, Allah Hafiz, have a nice day, and bye-bye. See you all tomorrow. I'm ending the meeting.